All right, this is 7.4.1, capacitance. We're going to start by talking about what capacitors are, what they do, and then later on we'll look at the capacitance equation. So, our capacitors, these are electrical devices that essentially store charge and energy, similar to a battery or a cell. So these store charge and energy. And essentially, what a capacitor is, are two metal plates that are insulated between each other. Now, the symbol for capacitors, the electrical symbol for capacitors, looks similar to that of a cell, but instead of having two parallel lines where you have a long and a short line, both lines are the same size. So let's draw a circuit that can be used to charge a capacitor. So here we've got our two lines. And we plug this into a cell. We'll give ourselves a switch that enables us to charge and cease charging. The cell has positive and negative terminals. So if we use this cell to charge this capacitor, the plate that's connected to the positive terminal of the cell becomes positive, and the plate that's connected to the negative terminal of the cell becomes negative. So these become charged positive and negative. And if they become charged, well, charges create an electric field. So there is an electric field between those two plates, which you've learnt about already. So here we've got an E field.
So in this case, they haven't been polarized.
In this case, we're not talking about polarization yet. We're going to talk about that another time. So this is the most basic form of a capacitor. Two parallel plates. Now, if you use the potential difference from this cell to charge this capacitor, then the potential difference across the capacitor has to equal to the potential difference across the cell. So V capacitor equals to V cell. When it's charged. Until it's charged, current is going to flow in this circuit when we close the switch until the potential differences become equal. Or, we can also say, until the capacitor is fully charged. So this is after fully charged. And then I'll write here, when switch is closed, current flows until capacitor is fully charged. Now let's have a look at the diagram and analyze it a little bit. If the potential difference of the capacitor is now equal to the potential difference of the cell, they're both in series with each other, but notice how the positive terminal of the capacitor is facing the positive terminal of the cell. So it's similar to putting two cells in series but facing them in the opposite directions. So facing them against each other. The two potential differences are competing to push charges in opposite directions, so no current flows. If we look at the directionality, if the cell has a forward direction, or a clockwise in this case, direction for the potential difference, or is trying to push current in the clockwise direction, the capacitor is trying to push current in the anti-clockwise direction. So their potential differences, they cancel each other out, and that doesn't allow any current to flow. Now, capacitors have a quantity called capacitance. This is their ability to store charge. The bigger the capacitance, the more charge they can store. So, capacitance. We use the symbol C. This is the ability, to store charge. It depends on the area of the plates. It will depend on the separation of the plates, and it will depend on any material placed in between them. So, depends on, and I'm going to use bullet points of a bullet point. So, depends on area of the plates. So if you have a large area, that means you've got more space to store charge. If you have small areas, less space to store charge. So it depends on the area of the plates. It depends on the material between them. So if the material between them can easily break down into becoming a conductor at larger potential differences, then at that point it can no longer store charge, because charges will jump across. So think about two parallel plates. If we make potential difference very, very big, at some point charges are going to jump across the gap. They're going to break the air down in between it. The air is going to behave like a conductor, and any material will break down eventually and behave like a conductor. But some materials are better at not doing that than others. So they're better insulating.
So you use like cardboard or something?
You wouldn't use cardboard, because cardboard will burn.
What?
You'd use a wick, and in the wick will be a liquid called electrolyte. But we're going to get onto that. That's again another lesson. So the material between the plates. And the separation between plates. The capacitance of a capacitor does not depend on the potential difference.
So it doesn't depend. So when you see the material of the plates, you mean the material in between it?
In between the plates.
Okay. Okay, so not the plates themselves.
Yeah. So the plates themselves are just metal, but the material in between should not allow the charges that build up on the plates to jump across one plate to another. Because once they start jumping, that's a current. And if there's a current flowing across the plates, then you're not storing charge. You're not building up a charge. You're letting it flow. Like if I took a metal wire and put it between the plates and it touched the two plates, I can't store charge.
Yeah.
What is touching the two plates? Well, the air in between is touching both plates. But air is not a good conductor. It's an insulator. However, at very large potential differences, even air can turn into a conductor, like you see with lightning.
Okay.
Yeah? So we put other materials in between to make sure that doesn't happen. Okay. So the charge stored on a capacitor is proportional to the potential difference applied. If we were to graph this, V against Q, we get a straight line. So there's some property of the capacitor there that makes it proportional. That's called the capacitance. So in this case, Q is equal to CV. Q is the charge measured in coulombs. C is capacitance measured in farads. V is potential difference. Measured in volts. Now, in terms of quantities, 1 farad is very, very big. It's a very large capacitance. So most capacitors will be in the range of microfarads or millifarads. Let's do an example. A 300 millifarad capacitor is connected to a 15 volt DC supply. Calculate A, the charge stored when fully charged, and B, the number of electrons stored on the plate. You can pause the video here to attempt the questions and resume the video when you're ready to see the solutions. Okay, let's solve these questions. So for the first question, we want to work out the charge stored when it's fully charged. So we're simply going to use the capacitance equation, Q equals to CV. Now the capacitance given is in millifarads, so we have to make sure that we've converted that into farads before putting it into the equation. So that's 300 times 10 to the minus 3, multiplied by the potential difference applied, which was 15. That gives us a charge of 4.5 times 10 to the 3 coulombs. Times 10 to the minus 3. Did you type it in wrong?
Give me. Is it 4.5? Yeah, so 4.5.
Just 4.5. 4.5 coulombs. Right, part B, the number of electrons. Now we know that if charge is being accumulated on a plate, that's because electrons are being accumulated on a plate. So the charge that's on the plate is equal to an n integer number of electrons multiplied by the charge of an electron. So let's write that down mathematically. Q is equal to N times E. So if we want to work out the number of electrons, we're going to rearrange this to get N equals to Q over E. So we've got 4.5 coulombs all over the charge of an electron, which is 1.6 times 10 to the minus 19. That gives us about 3-ish. Is about 3 times 10 to the 19, approximately.
Yeah, 2.8.
2.8. So that's 2.8 times 10 to the 19. And this is a dimensionless because we've done charge divided by charge. Also, the number of electrons does not have a unit. It's just the number of them, how many of them there are. And that's the end of 7.4.1.